We'll continue now with discussing chi-square distributions and multiple proportions. The essential questions are: what is the decision rule for you to use a Fisher's exact test to test multiple proportions? And if you use a Fisher's exact test, what statistics do you report in your write-up? Remember, if under the assumptions for sample size, you determine that more than 20% of your cells have an expected value less than 5, then your sample size assumption is violated. This is the rule of thumb. More than 20% of cells have an expected value less than 5, not an observed value, but an expected value. There are 3 options. Ignore your results on the sample size test. That's a bad idea. In fact, it's such a bad idea that software warns you when it happens. That should be your big indicator. Collapse your cells if you can. So if you only have a 2x2 table and you violated the sample size assumption, then your only option is to do a Fisher's exact. If you have multiple response levels, 3 or more, you can maybe dichotomize it. So take 3 groups down to 2 groups, or you could take 5 down to 4 or to 3 or ultimately to 2, if it makes sense. So your variables need to have some kind of order to them for that to make sense. For example, if your options were chocolate ice cream, vanilla ice cream, and strawberry ice cream, it would be hard to dichotomize those. But if you had really thought about it, you could do vanilla versus other ice creams. So really put some thought into the collapsing of cells. What you don't want to do is simply collapse cells that have small n to make bigger n. Because you wouldn't want to, say, if you had temperatures, the low temperature, medium temperature, and high temperature, you wouldn't want to collapse low temperature and high temperature just to meet the sample size assumption. That doesn't make sense. So really put some thought into the design of the question and what cells you could collapse. Or you could use a more complex statistical method, and this is a Fisher's exact test. Recall in the ECMO study, looking for participants that survived to 1 year, they were asked if their health status was better, somewhat better, about the same, somewhat worse, or worse than the prior year. And we saw those results in Table 5 of the paper. Remember, we had to adjust the sample size from what was in the paper. We're looking at the conditional, so 52 in ECMO, 31 in conventional management, with an 83 N of overall. We had this contingency table, so this showed all of the proportions by group. This was what our jump data table looks like. We have 2 treatment groups and 5 responses. That gives us 10 cells, which then gives us 10 rows. Now remember, here in jump, in fit y by x, under the red arrow in the contingency table, you want to click expected, and we found that we had 3 cells out of 10 that were expected less than 5, so we were in trouble here. In the prior example, we collapsed them to be better, same, or worse. In this example, we're actually going to go ahead and do the Fisher's exact test. Steps 4 through 6 remain the same, with the simple alteration to step 4, that our test, instead of chi-square, is Fisher's exact test. So step 4 is pick your statistic. Ours is a Fisher's exact test. Step 5, again, think about observed minus expected. If our observed and our expected are close, then we expect zeros in those differences. And a small total in a Fisher's exact as well will lead us to go with the null hypothesis. Large deviations from what we expected, or if this is what we saw as rare, then we would go towards the alternative. Step 6 is our universal decision rule. This stays the same. This will be the same for everything we do. Pick the null hypothesis when you have large p-values, if those p-values are larger than alpha. Pick the alternative with small p-values, or if those p-values are less than or equal to alpha. Step 7, calculate the test statistic. All software should have a Fisher's exact option. Remember, it's standard in JUMP with the 2x2. It pops up. You don't have to ask for it. When you have a larger than 2x2 table, also called an R by S table, rows by cells or row by column, so R by S, you have to fit Y by X first, and then you ask for the exact test, and then you ask for Fisher's exact test. If you get the pop-up warning in JUMP, this happens with large tables or with a lot of low number cells, it will take a lot of time to calculate all the possible options. Remember back to our simulation that we did and calculating all the possible ways this data could turn out. That can take a long time. So click continue, and you may have to wait. It's best if you close out all other programs while you're doing this and make sure you've saved everything and saved everything in JUMP. You can always go back and click continue after you've done that. Once you click continue, it may take some time and you ultimately may end up quitting JUMP because your computer does not have enough space or memory to compute the Fisher's exact. In that case, either find a larger, faster computer or find a statistician that can do your Fisher's exact for you in SAS. If you have the frequency table, it should be very quick to do it in a program like SAS that has a large memory on that computer. Those are usually pretty quick. In most cases, it should just take a few minutes or be near instantaneous in JUMP for the Fisher's exact test. Once you've calculated the statistic, get your p-value and make a statistical decision. Note that with multiple proportions, you are only going to see a single p-value. There are no one-sided tests given here. That's because we're looking at multiple proportions. So we're not going to test P1 greater than P2 greater than P3. We're going to test P1 equal to P2 equal to P3. That's our only option, is equal or at least one difference large enough to say they're not equal. Get your p-value, make your decision. Remember, large p-values go with the null hypothesis, small p-values go with the alternative hypothesis. Then you'll go to step 9, put your decision in words, and step 10, you will write it all up. You must say you did a Fisher's exact test. You can get away with saying you did a chi-square, but really you should specify if it was likelihood ratio or Pearson. Remember, we prefer the likelihood ratio chi-square test, but you absolutely must say you did a Fisher's exact test. That goes to the assumptions. If you don't say a Fisher's, it's assumed that you met the sample size assumption. So if you did a Fisher's, say you did a Fisher's exact test and give that p-value. Up next, we'll review how to test multiple proportions in JUMP, and we'll review the 10 steps for testing proportions overall.